Hello everyone, in this video we will see how to control DC motor using Raspberry Pi Pico board and TB6612FNG H-bridge motor driver. This motor driver is smaller in size when compared to other H-bridge drivers like L298, this doesn't require heat sink. This has two separate voltages for motor and logic. Logic voltage can be 3.3 volts, which makes easier to interface with Raspberry Pi boards. I am using BODC motor for this demo.
Let's look at the pinout of TB6612 motor driver. This is a 2-channel motor driver which can control 2 motors. This board supports 2 different supply voltages. One is for motor voltage. This is a VCC motor. This can take up to 15 volts for the motor. Another one is a logic voltage. We can give 3.3 volts or 5 volts, depends upon the microcontroller board which we are using. Apart from VCC and ground, it has other pin called as a standby pin. This should be made high to enable the function of the motor driver. In my circuit, I am connecting directly to the logic voltage, and if you want to control the function of the driver from the microcontroller, you can connect to the GPIO pins also. And IN1, IN2 and PW are the control pins for the channels. Each channel has 3 controller pins. IN1 and IN2 are used for controlling the direction of the rotation, whereas PWM is used for controlling the speed of the rotation. These two are the output pins of the motor driver to which we can connect the motors. So this is the channel 1 output and this is the channel 2 output. Let's look at how the connections are made between the motor driver and the Raspberry Pi Pico. So GPIOs of Raspberry Pi Pico 16, 17 and 18 are connected to the control pins of the motor driver IN1 and IN2 and PWM. By controlling the logic levels of these pins, we can control the direction of the rotation and the speed of the motor. Apart from these control pins, the standby pin is connected to the logic voltage, and motor voltage is connected to the 5 volts, and logic voltage is connected to the 3.3 volts, and ground is connected between the boards. So this is how the connections are made, and I'll provide the detailed schematic diagram for these connections. Before going to understand the coding part, let us see what is a pulse width modulation. PWM or a pulse width modulation is a technique used to generate variable voltage from digital IOs. PWM generates the pulses shown here. So if you look at the pulse, it is 50% on and 50% off. So this is called as a 50% duty cycle pulse, and this is the time period of the pulse that is generated by the PWM. So generally these microcontrollers provide an option to provide to specify the time period and the duty cycle. So if you specify duty cycle 70%, that is the active part of the pulse is 70% and off part of the pulse is 30%. So if the voltage like VCC is 5 volts maximum, so you get 70% of 5 volts, that is approximately 3.5 volts as an average DC voltage when you generate a PWM of 70%. So by using this PWM, we can generate voltage ranging from 0 volts to VCC max. If it is a 5 volts, you can generate 5 volts with a PWM of 100% duty cycle. So the duty cycle minimum can be 0% and maximum can be 100%. So like this Pico microcontroller also provides an option to provide option to specify the frequency and PWM duty cycle of a particular GPIO which we are using to control this speed of the motor. Let's look at the MicroPython program to control motor driver using a Raspberry Pi Pico. From MicroPython machine library, we are importing pin class and PWM class. These two are required for controlling the GPIO pins of the Pico. And we are also importing sleep library This is required to implement the required delays in the later part of the code. So here what we are doing is we are taking the instance of this pin class with the GPIO pin 25, which is connected to onboard LED. And similarly, we are taking instance of INA1, INA2 using the GPIO pins 18 and 17, which are connected to the motor driver. So to use the PWM functionality of the Raspberry Pi using MicroPython, we have to take instance of this PWM class with the particular pin, which is PWM pin 16. We connected to the PWM of the motor driver. So PWM has a different parameters to be mentioned as I explained. So one is the frequency. We are setting the frequency of 1K, and we are toggling the onboard LED, which is like we are making it on. Here I am implementing three functions. One is rotate clockwise, rotate counterclockwise, and stop motor. So these two functions will take the duty cycle as argument. So this duty cycle can be from 0 to 100%. So 0 is like a 0 voltage output to, and 100% is like the maximum motor voltage we will get. So as per the data sheet, to make the motor to rotate in a clockwise direction, we have to make IN1 and IN2 as like 1 and 0. So you can get these values from the data sheet of a TB6612. And duty cycle, whatever the duty cycle we are passing to these functions is like percentage. Now we are converting this duty cycle into the microcontroller value. Because this is a 16-bit PWM channel that is supported in our Raspberry Pi Pico. So for a 16-bit PWM channel, the maximum value is 65,536, which is 2 power 16, and the minimum value is 0. So whatever the duty cycle percentage we are getting, we are converting into the 16-bit value and passing to the PWM duty U16 function. So similar to that of the previous one, here we are implementing a counterclockwise function where INA1, INA2 should be 0 and 1, which is like reverse of this clockwise rotation. And the duty cycle, similarly, we are getting percentage of the duty cycle here, and we are converting into the microcontroller channel value and passing to the duty cycle function. And stop motor. So here to stop the motor, we have to make IN1 and IN2 0, and duty cycle also we are making it 0. So this is the main loop actually. So what we are doing is we are continuously keeping in the while loop and accepting the value from the user. So accepting the PWM value from the user, which is in the form of percentage, like user can enter 0 to 100%. So we are printing that value. So that duty cycle value we are passing to the clockwise rotation function. So so once the duty cycle is passed, it will be calculated to the integer value, and motor will be set to the clockwise rotation. So we are sleeping for 5 seconds. It means the motor will continue to rotate in the clockwise direction for 5 seconds, and then we are invoking counterclockwise rotation function. Then motor changes its direction and rotates for 5 seconds in a counterclockwise direction and continue to rotate for 5 seconds, and then we are doing the stop motor. Then again the program will go to the main loop asking for the new PWM value. So this is how the program we have written to showcase the functionality of PWM and a motor driver connected to the Raspberry Pi Pico.
Now let us run the program. So this is how the circuit is connected. I have put one wheel on the motor so that we can observe the speed of the rotation. So let us run the motor with the different PWM values and see how the speed of the motor varies and its direction. So now I am giving PWM of 20% duty cycle. So motor start rotating with less speed because I am giving 5 volts and the 20% it is 1 volt to the motor. So now I am increasing the duty cycle to 40%, that is 2 volts. According to the code, actually it runs in the clockwise direction for 5 seconds, and then it turns it in the counterclockwise direction for 5 seconds and then stops. So this is how we have written the program. So then let us increase the PWM to 100%. So this is a 5 volts. Now we are applying 5 volts to the motor. Then let's go back to 15% PWM. So this is like approximately 0.75 volts, and motor is rotating very slow. So let us see if I give 10% of the duty cycle. So that is 0.5 volts. This is how we can use TB6612 motor driver and Raspberry Pi Pico to control the DC motors. These kind of motor drivers are used widely for 2-wheel drive and 4-wheel drive robots.